All right, class. So the specialized cells, they generate the action potential, right? And these cells are called the pacemaker cells. Now, we have learned that the pacemaker cells are autorhythmic in nature. To start with, let's think of the neurons. When talking about the neurons, do you remember we mentioned that neurons have a resting membrane potential at -70? Then -55 was threshold. Do you remember those? Okay. These specialized cells of the heart, they do not maintain a resting membrane potential. This is something that you must remember. They do not maintain resting membrane potential. And the event starts at -60 millivolts. So let's start here at -60. Now, these specialized cells have some special so let's draw a specialized cells. Let's say this is a specialized cell. And when the event starts, it's at -70 millivolts. Remember, it does not have a resting membrane potential. Okay. Now, at -60, the first thing that happens is there are some specialized cells, specialized channels called Hcn channels. These channels open. And as these channels open, sodium slowly enters the cell. As sodium comes in slowly, it brings in positive charge, right? And this is called pacemaker potential, also known as diastolic depolarization. And then sodium rushes in until the inside becomes -40. So from -60 to -40, we call it pacemaker potential or diastolic depolarization. And this is caused by slow entry of sodium through the Hcn channels. If you look at the graph, so we start at -60 and we move all the way to -40, right? So during this time, what's happening? The membrane potential is changing to less negative, more positive due to entry of sodium ions slowly via the Hcn channels. These channels are also known as funny channels because, they open due to hyperpolarization. Okay, so right at -40, what happens? At -40, voltage gated calcium channels open up, and so at -40, now it's at -40, and at this point you will have all these voltage gated calcium channels open up. And as these channels open, what rushes in? Calcium. So now you will have calcium rushing in. Calcium carries positive charge, so obviously it'll depolarize the cell to about +20. And then at +20, the voltage gated calcium channels close, and we have our favorite voltage gated potassium channels open up. And then potassium leaves the cell, and that results in repolarization of the cell back to -60. Okay, so let me draw this again. So now we have a lot of calcium inside, and the membrane potential reaches +20. At +20, these calcium channels are closed, and then potassium channels open up. As potassium channels open up, what leaves? Potassium leaves. As potassium leaves, we are losing positive charge. So the membrane, the inside, becomes negative, and that helps the membrane potential to come back to -60. And once it hits -60, same thing is repeated. sodium enters slowly through these Hcn channels, and then once the membrane potential reaches -40, you have the voltage gated calcium channel open, and calcium rushes in, causing depolarization up to +20. At this point, the voltage gated calcium channels close and the voltage gated potassium channels open, resulting in repolarization, and the process is repeated over and over and over and over. This helps to maintain the diastolic depolarization, and as these action potentials are generated by the pacemaker cells, that results in the spontaneous depolarization of the atria. All right, hope that's clear. So we know that the pacemaker cells are autorhythmic, right? They don't need any stimulation of the nervous system. However, if you are this close to an accident on the freeway, what happens to your heart rate? It paces up, right? Because your heart is under, there is autonomic innervation. So let's say this is your heart, and it has autonomic innervation. It gets innervated by the sympathetic nervous system, and as the sympathetic nervous system innervates the heart, it results in increasing heart rate and increasing heartbeat. The heart is also innervated by the parasympathetic nervous system, and the parasympathetic calms down the heart. Remember, the parasympathetic is associated with rest and digest. It helps the heart to calm down. Okay. The sympathetic nervous system releases epinephrine and norepinephrine, and that increases the pacemaker potential and the cardiac rate. So the sympathetic system has norepinephrine and epinephrine. The parasympathetic neurons release acetylcholine that opens up more potassium channel and slows down the heart rate. Okay. Oh, one last thing I forgot to mention. Under the effect or under the influence of this epinephrine and norepinephrine, the Hcn channels open, and then there is faster inflow of sodium ions. So if I draw it out, so -60, right? -40, +20, -60. So when the heart is under the influence of epinephrine and norepinephrine, what happens is this thing is faster. So the Hcn channels and diastolic depolarization is faster because a lot of sodium is rushing in super fast. It's not slow. And then you have this followed by this, followed by this. It's kind of faster. So that helps to pace up the heart. And when it's under the influence of the parasympathetic neurons that secrete acetylcholine, that opens up the potassium channels. Remember, depolarization is caused by potassium channels. So these potassium channels are open longer to slow down the heart rate. That's the difference. All right. So we just finished talking about the action potential of the specialized cells. Now we are moving on to the action potential of the myocardial cells, which look very, very different from what we just saw. Remember, we are looking at the myocardial cells, and these are the contractile cells of the heart. These are the contractile cells of the heart. Okay. I want you to, before I start talking about the action potential here, I want you to remember one thing. In case of myocardial action potential, there is no threshold. Absolutely no threshold. So, what happens here? The myocardial cells, they maintain a resting membrane potential at around -85. So -85 millivolts is their resting membrane potential. And do you remember that we mentioned the specialized cells are connected to each other by gap junctions, and the specialized cells are even connected to cardiocytes or myocardial cells by gap junctions, and the myocardial cells in turn are connected to each other by gap junctions. So the point is, every single cell is connected to other cell by gap junctions. So if you can think of it like this, the action potentials are generated by the specialized cells, right? And the action potential flows via these gap junctions and reaches the myocardial cells. Fun! As soon as the action potential reaches the myocardial cells, what happens? Voltage-gated sodium channels open. Voltage-gated sodium channels open, and sodium comes in. Sodium comes in. As more and more sodium rushes in, obviously there is depolarization because sodium brings in positive charge, and the membrane potential reaches about and the membrane potential reaches to about positive 20. Positive 20. Okay. At that point, the voltage-gated sodium channels close, and there are some fast voltage-gated potassium channels that open. And when these potassium channels open, they are fast channels. A lot of potassium goes out, and then the membrane potential comes down to about -15. And at this point, there are voltage-gated calcium channels that open up. These are slow calcium channels. So these channels open up. And as the calcium channel opens up, calcium rushes in. Calcium rushes in, and then potassium is leaving, right? So that balances out. And this plateaus at -15 millivolts, and it continues for about 200 to 300 milliseconds. At this point, the voltage-gated calcium channels close and the voltage-gated potassium channels open, and potassium leaves the cell, leading to repolarization. I'll stop here and then make another video where I'll hand draw things. Hopefully that will be more helpful for you.